My name is Ben Dewey. I am a practice director at Toulon. We're an IT consulting company with offices all over the country. And today I'm here to talk to you about asynchronous application development within .NET. I don't know if either of you were in my previous talk. Similar to that, it's going to try to tell a little bit of a story to bring you through a little bit of the history that we have within the .NET framework on async patterns to bring us all the way to where we currently are, which is the async and await keywords, which really is just a ton of magic that happens. At the end of this talk, and really the reason why it's advanced, was because we're going to go into the compiler and we're going to look at some of the tricks that are happening there to really understand the pros and cons of using async and await. Because while it is very powerful, you can misuse it and then get yourself in trouble as well. So my hope is that by telling you the story, it gives you some clarity to it, but also provides a little bit of an understanding of why you would want to use it in certain places and not. So as I mentioned, we'll start off with just the basics of asynchronous application development. We'll start talking about tasks, and tasks themselves was really a new paradigm that was released in .NET that was the core to async and await and those keywords. Without it, we wouldn't be able to do the things that we're doing. Have a few samples, and one sample in particular that I wanted to show off that you guys might be able to take and look at home and understand a little bit more of some of the techniques and patterns to using async and await. And then we'll go into the fun stuff, which is that compiler legwork, and understand the magic that's happening underneath the covers. And then I'm going to end with a few tips and tricks. And since it's the last session, last day, I might try to get you guys out a little early, if possible, so you guys can go enjoy the rest of your night. OK, so as far as asynchronous scenarios, there's a couple core ones that come up very commonly within application development. The first one is just disk I/O or network I/O. You need to go out to call a database. You want to read something from the file system. You want to read something from a network share. All these tasks take time. Microsoft actually defines it in the Windows 10 UWP applications that anything that's over 50 milliseconds, which is extremely short, should be asynchronous. So disk I/O and network I/O are one of the most common ones. We also have with any UI framework and UI paradigm, they generally have a single UI thread. And that UI thread, the main purpose of it is for responding to things that happen on the UI. So when I click a button, I need that click event to fire. If I'm doing something on that thread, then that click event doesn't fire. And as I'm sure you guys have all seen the Solitaire screens that we used to get in Windows, that is because somebody was doing some coding or running some CPU logic on the UI thread. Therefore, the UI wasn't able to respond to events that were actually happening. The other one is really taking advantage of multiple cores. So most machines these days have 4 cores, and if they're hyper-threaded, it's emulated into 8 cores and upwards of more in that on servers. And we need to take advantage of that. If we're writing very linear sequential code, then you're not able to take advantage of that. So by writing code, especially CPU-bound code, on multiple threads and as multiple tasks, it allows the thread pool to go ahead and distribute that up across all the different threads and kind of basically cut that time down by the number of cores that you have. The final one is for kind of fire and forget scenarios. There are some scenarios where you want to just let some event happen, and I don't really care about the results from it. It's a little bit dangerous, but I wanted to note it here anyways. And we'll talk about some of the reasons why it's dangerous later on. Mostly in exception handling, but. So within .NET, throughout history, there's been a couple different ways in which you could do asynchronous work. The initial way, which was the APM, or the asynchronous programming model, was the main way things were written in the .NET framework. So if you look at streams and network I/O in the beginning, they were all using this event async pattern. And essentially, that's the technique where you have a begin and an end, right? So in the case of reading something from a stream, you'd say begin read, and then you'd have a callback function. And once the callback function was fired, you'd call end read, and that would allow you to have an asynchronous loop or asynchronous operation on a stream. With UI frameworks and a couple other places this seemed to pop up, they started going with an event-based pattern. And the event-based pattern was also showed up in add service reference. So if you ever did add service reference, you'd see this as well. But you'd go ahead and set a completed event handler, which allowed you to also have multiple event handlers, which in some cases had problems. But from there, you'd call an event, and then once that event was completed, you'd get a callback into your event handler. All right. The last one is really not asynchronous at all. It's actually synchronous, but it comes down to that ability to spread things across multiple cores, and I wanted to mention it here as well. And that's really just kind of more background threads and that mentality of I want to maybe just take something and put it off of the UI thread, or I want to take something and distribute it across multiple cores. And we're going to treat that as a type of asynchronous pattern. All right, so let's just kind of do a quick little level set review on some of those. So here we have just some basic code to read a file from a file system. So here we have a file called temp.txt, which is in our temp directory, and we're creating a new stream, and we are just getting the string data from that, we're reading in the stream into a buffer, and then we're getting the string data from that buffer. Can everybody see this okay, or should I make it bigger? Crickets, I guess that means it's okay. Okay, one thumbs up. All right, you voted for everybody. All right. So this is not asynchronous at all. This is synchronous. It's going to block your thread until that comes back. There's actually an interesting story once in an intro to kind of computing program, and I'm going to just pause a second and digress a bit into that. But this idea of these two simple lines, console.write and console.read, right? These two, for the most part, seem like fairly innocuous and fairly similar lines of code. But the reality is they have drastic differences in the way they behave, right? Console.write line just executes and moves on to the next line of code. Console.read will actually pause there, similar to like a thread.sleep would. It's sitting there, and your application is not going to continue on. So in this case, this is all synchronous, and it acts in that same way, where it's going to read the stream, and if that file is locked, or if that file is a large file, a number of things can happen, but essentially your thread is blocked there until that file is done reading, in which case you can continue on. So a much better way to write this type of code is to do asynchronous, right? And streams, being in the .NET framework since the beginning, use that initial pattern that we talked about, which was the async programming model, which has begin and end. And what we have here, and despite your vote, I'm sorry, I'm going to make it a little bigger just so you can see it. So we start off with defining a callback, right? So this callback is what we want to execute when the stream is actually, after the stream has finished its reading process. So instead of blocking the thread, it's going to instantly continue on and then call back into this function when it's done. So in this case, we're going to just call begin read, and then as an additional parameter, we will pass in the callback function. When the callback function calls, the main thing that's passed into that, or the only parameter that's passed into that, is an async result. And this iAsync result is sort of like a correlation ID. It's a way in which I can tell the stream end read, well, what am I looking for the end result of? So it correlates it with the begin call, and that's how I get the actual buffer here in the bytes that are read. Sorry, the buffer actually came in as part of the begin read. It was filled as I passed it in. The bytes read is just the count of the integers. And then from there, I can continue on. Now, what's interesting here, and you're going to see kind of popping up as we go along here, is the time at which this ends. Okay? So this method here, when I call into this read file APM function, doesn't end when the file is done reading. It ends as soon as I start reading. Right? So as soon as I call begin end, this function actually ends and returns back to the original caller, and the program continues along on its way. It comes back later on. In this case, it's going to come back on the same thread, but you'll see in other patterns where it may not come back on the same thread. And what's going to happen is you're going to end up in a situation where if you aren't prepared for that, especially when you get into async and await, the logic is going to not flow properly. So you just want to be conscious of where the boundaries are for your different methods. But still, fairly simple in .NET from the core. Nothing crazy here yet. The next one is the event async pattern. And this one's also very something you've probably seen before. But we have a completed event, just like we did before. So instead of a callback function, we have a completed event. And that is registered using an anonymous function as well. And then we go and we call download string async. Now in this case, I'm not passing in any additional functions. It's registered at the client level, so at the original parent object, which is handling that. And then this is going to have the same scenario as before, where this method will complete as soon as we start downloading it. And then at some later point in time, this is going to be called back into this function. Now I'm using anonymous functions here, but this could also be an outside function. It actually might paint the picture a little bit better if I made it outside. Question?
In this scenario, is it going to come back on the same thread, or is it possibly?
With this one, I think not. Most of them, so generally speaking, for performance reasons, they just throw back on whatever. And in the case of Windows Forms and WPF, you always had to check if you were on the UI thread. So I believe, given that this one was still in the older ways. When you talk about the newer Async and Await, the default is actually to come back on the same thread, which has some performance implications that we can work around. But it is one of the tips that we come into later about knowing which thread you're coming back on. OK, the last one I wanted to talk about here is the background job. There's a number of different ways to do background jobs, but the one I wanted to show off here was queuing something in the thread pool. So the purpose here is I just call threadpool.queue user work item, passing it in some chunk of code that I want to execute. And the beauty of this is I'm not creating a new thread. I'm not spinning up, having to tear down and shut down that, or start up and shut down that thread. I'm allowing the thread pool to handle that for me. And what's nice is if the thread pool has 4 or 5 threads, then I could just use those that are already there. And it's also going to take care of being smart enough to create and shut down threads as it's needed. This here is really, when we get into tasks, this is really what's used in the covers in a lot of ways. There's a process that's managing the threads for you, and you think of your work as a task or a unit of work, and that allows you to really kind of focus in on what the work is and not on the thread management side of things. All right, so those are just the kind of basic samples. So next I want to talk about the task parallel library. This actually came out a little bit before this as a CTP, and we were able to use it and was able to even work within Silverlight, I think, before it worked in .NET. It originally shipped with .NET 4, and it uses the thread pool under the covers, and it uses that same concept of a work item, right? So I want to have a small unit of work or a small kind of chunk that I can then go and send off to the thread pool to go and execute. There's a couple methods on these tasks. In the case of the thread pool, we queued just an anonymous function. In the case of a task, we actually create a task, and then that task you can pass around, and you can start it whenever you want to. So you don't necessarily have to start it right away. You can delay the starting of it, or you can start it right away and then never listen and kind of listen towards the end for a completed event. There's a couple methods on here. Start, which is what we mentioned as far as kicking it off. So you can register, you can create the thread, create that unit of work, and tell it to start. The other one, which is very nice in terms of how do you start hooking these things together and understanding when things are completed, is a method called continue with. And essentially what that allows you to do is take a unit of work and chain other units of work to it. This is really going to be the main way in which we're going to have access into when a thread or a task is completed. So tasks don't have a completed event. They're not like EAPs. They don't have a begin and an end like the APMs. They are strictly that unit of work, and the only way you're going to get access into what happened as a result is to either use continue with or to synchronously access the result, which is going to block your thread, and we don't want to do that. A couple other ones when we're looking at as tasks and also some bit of synchronous and how do we kind of tell when things are completed. would be the wait and the when functions. So there's two calls that are easily confused. Wait is going to be a synchronous pause, whereas when is not. When is actually returning another task. But essentially, it allows you to hook up multiple tasks and understand what's happening between them. In addition, there's a bunch of extensions. One of the most common extensions are patterns in which allow you to convert things that are in the APM model or the EAP model and convert them over into tasks. So there's a couple extensions which are just one-liners, and I can say task.fromAsync, and it'll allow you to pass in a stream begin read and then an end read, and then convert that old mechanism into the new task mechanism. As far as those core libraries, though, .NET and then the Microsoft team has done a lot of work to go ahead and convert those over. But if you have your own custom framework, then you have the ability to migrate those fairly easily. What's important about the task parallel library is, in part of being the evolution into what we have now, which is async and await, was that really we couldn't have done the async and await without this mechanism to pipe things together and to continue by creating this chain of events. So when we get into async and await, we'll see how all they are is taking a method and having some syntax, but what it's doing is it's breaking up the bits where you have the await calls, and it's putting continue withs in between them. So let's jump over and look at a quick example of that. So here we have a basic kind of from-scratch version of a task. This is taking the event-based programming model, and it's essentially wrapping it in its own custom version of a task. There are extensions for this, but I wanted to show you kind of the manual way of doing things. And a lot of this code is all available, but a lot of it is trying to prove a point. So I wouldn't necessarily write this code because there's better ways to do it, but hopefully it illustrates what I'm trying to show you. So in this case, we're defining what's called a task completion source. And that source is essentially, it has a single property on it. It has a couple, but the main property on it that we're interested in is the task. And that represents an object or a bit of a promise, right? So if you're familiar with some of the JavaScript terms, this is a promise that at some point some work's gonna happen and you're gonna have a result. Now, from here, we can go off and do whatever we want. We can do things on multiple threads. We can do things on a single thread, or we can just use standard built-in async patterns. So that's what we've done here. I use the event-based pattern. And when the download string is completed, I take that original source and I say try set result. And that essentially means tell this promise that it's completed. And anybody who's listening now to this task can get notified or execute its continue with function to go ahead and proceed on to the next bit of work. All right? So this task completion source is really that kind of underlying object or promise that represents a task. Okay? So from here, this is another example that's not using the event-based pattern. This is actually using one of the built-in tasks and shows how you'd use continue with. HTTP client came out around the same time as tasks and was built with tasks in mind, as opposed to the previous version, which was built with the event-based pattern in mind. So here, what we're doing is we're going to call getAsync, which is actually going to return a task of an HTTP response message. So this task here, if I look at it, I can look at things on here. So I can look at the .result, right? And if I look at the result, what's actually going to happen is it will synchronously halt that thread until the result's completed and show me the result. But we don't want that. We also have other options here. We have continue with. We have configure await, which is a very important one that we can come to later. We also have the exception, which again synchronously pauses until something's done. And then this one here, which is completed. And what is completed is it actually represents a task that has not been, or it tells you whether the task has been completed. So there are scenarios where you can make optimizations in your code if the task has already been completed. So you can go ahead and set up an anonymous function and do a bunch of work to set up your continue with, but if the task is already completed, then that's really not necessary. So you can check that flag and execute different logic, and we'll see how the compiler is using that exactly to do that. And then there's a status, which also, similar to is completed, tells you what the state of the task is. Status can also be faulted, and there's a couple other scenarios that can be, or options. All right, so from here, after we get this task, considering in this scenario we don't have the async and await keyword, the only real option, if we don't want to be synchronous and block our thread, is to call continue with, and then pass in an anonymous function there that's going to execute as soon as that task is completed. So in this case, our content task, or our HTTP client task, we're saying when that completes, continue with this anonymous function, passing in the original task that was executed. So in this case, this TR is going to be the HTTP client task. Now from here, I can confidently check the result without blocking the thread because we're guaranteed the task is completed. And then we can go on further and read the string from it and then chain these together. The last method on here is called unwrap. And what that essentially does is it allows you to take a chain of multiple tasks and kind of unwind that. So if we look at the actual result here of this one, let's just set this to something else. So the actual result here is a task of a string, right? So by default, when you do continuations, it chains those all together. And so this is still returning the original task, but inside of there, it's a different task. And if you want to kind of break out of that, they've provided a helper function on top of the tasks, which is called unwrap. And what that'll do is that'll get you the very last task in the continuation as opposed to a bundle of all the tasks. Okay? So this stuff is, what we had in the kind of initial release of tasks without any async and await. And then we'll get into the async and await next. Okay. So async and await keywords. I may have had that wrong, actually. The async and await keywords were actually part of the CTP that was released in 2010. The official release was in .NET 4.5 back in August 2012. And essentially it allows you to take the features that you have within tasks and the continuation and allows these nice convenient keywords that really kind of makes you feel like you're taking something that is very asynchronous and nested with all these anonymous functions and feel like it's very synchronous code. It also provides a nice synchronous debugging experience, which makes it really nice too and is actually quite complicated to do. All right, so let's show how that changes now. So you guys got a peek of it already. But we have here this original code which goes out and gets our weather and then returns our result. And what we have here is the same code but using async and await. So immediately you see the lack of all the nested, all these tasks that we have to do, and it seems very logical the way this code works. In order to make this work, what we're doing is we're adding two keywords. The first one is on the method, and in this case we're putting an async keyword on the method. And whenever you add an async keyword, you need to have a return type that's of a task. The only exception to that would be if it's an async void. So async void is also acceptable instead of actually returning the task. But async void should actually be avoided if at all possible. One other thing to note here with async void is that async task here and async void are completely interchangeable. I can't type. But in the case of this one, I'm returning a string. But in the case you didn't have a return variable, you could interchange async void and async task the same way. And it's always recommended that you return async task because that will maintain your exception stack, which you generally want. The only case where that's not true is in event handlers. Unfortunately, event handlers have a void return type, and you're kind of stuck using async void in that case. Okay, After that, we are going to call into our task here. And so this get async is going to return a task. And by putting the await keyword on there, it's kind of, I know I used this word unwrap earlier, but it kind of wraps and unwraps things. So you can kind of think of the async word as wrapping it and the await word as unwrapping it, right? So in this case, this method here, download whether async, is actually returning a string, right? So when I add the async keyword, I have to wrap it in a task of a string. Await does the opposite, right? So this here returns a task of an HTTP response message. But when I put the await keyword on there, now the result is an HTTP response message. So the await keyword takes the tasks off, and the async keyword kind of adds them on. Okay? Finally here, we have two async methods in this case, and we're calling async, get async to get the response message, and then we're calling await for our response to read the string async to actually return the string. Again, in that case of kind of wrapping and unwrapping, the result here, if we look at this, this is actually a string. I'm having trouble typing here. All right. So the result here is actually a string object that I'm returning. Right? So at first glance, why can't I do this correctly? It seems a little bit odd that my method has a return type of a task of string, but the actual result that I'm returning from the method is a string. So just kind of bear in mind, especially when you're trying to troubleshoot some of the errors that you're getting, that that's happening a little bit automatically, and you may not notice it. Okay. There was another async that I want to show here. So here I have a slightly different example that shows some of the same concepts, but more on the background processing side of things. So here we have a simple WPF app that's just going to write a bunch of rectangles to the screen. Actually, let me make it smaller. So when I call run sync, I can move the screen around and nothing's actually responding, right? So I was actually doing it, but it didn't actually respond until it was actually fully completed. So that's an example of where we're kind of blocking the thread. The other example of running tasks async, you'll see that now running a task, which is going to be the same as async, the application is still fully responsive. I think every time I've done this demo in the past too, I end up remembering that there's a feature in Windows where if you shake the screen, it minimizes everything. But so you'll see that the app is still responsive now. And then the last one that I want to show off is when I get to the code, you'll see how we can take something with its async and run it across all the cores and really optimize it. So this one I'm calling run full throttled. And you see that now popping in things all over left and right because I haven't just said, wait on the creation of the rectangle and then create the next one. So I wanted to show how this code works as well. All right. So the synchronous one, fairly straightforward. We get a bunch of blocks, which is just really an object that defines the size of them. And then I called this add rectangle method. And this add rectangle just does a little bit of a sleep to kind of portray what it would be like. And then it goes and adds the rectangle to the UI, which is just a standard WPF call to add a control. So that's obviously the bad way. We don't want to do it that way. We don't want to call thread sleep in our code. The next method is using a task, right? So here, in order to make this work, we're starting to see where tasks really started to break down. When I showed the first example, we'd go out and get the weather, and then I wanted to come back. What we have here is we have a for loop, right? So in this case, I have an array of blocks, and I want to add them to the screen, right? But I want to set up a continuation. So I want to say when you've added to the screen, then continue with adding the next one to the screen, and then continue with adding the next one to the screen, right? So that for each loop becomes a little bit difficult to manage. And that's what we have here. So we've set up an anonymous function here, which is just an action. And we've called this add block task. And this add block task is actually, and the reason it's defined like this, where it's a null and then it's defined on a new line, is because it's actually a recursive function. So what we're saying from here is go ahead and add the rectangle as a task, and then continue with calling the same function, calling yourself with the next item in the for loop. All right? And so you end up taking something that was a for each loop and having to turn it into a recursive function in order to kind of get the continuation functionality that you actually want from that. All right, so and then you have to kick it off in order to start it. Question?
You could have done this by swapping thread sleep with task delay, right?
Yes, but that would have not paused the thread. So task delay actually doesn't halt the thread. If I did task.delay.wait, then I could, but yes, thread.sleep. Task.delay actually is far more performant than thread.sleep. And actually, I have seen someone do, instead of task.delay, they did a new task, thread.sleep.start, right? So they created a task that slept a thread. But yeah, task delay is actually smarter than doing that. All right, so what's really compelling about the async and await keyword is that simple functions like for each and simple kind of logical operators that we're used to just work. And so we're able to take something where we have here a single async and a single await, and we're running a for each loop over this. I didn't have to create any recursive functions. It just all automatically works and just looks nice. All right? Now, in order to optimize this and take this from something that's just a kind of synchronous continuation of adding rectangles and turn it into that full throttled, is actually just a one-liner change, right? So instead of here, where we were saying await, oh, I can't do it right, but instead of awaiting on this, what I'm doing is I'm adding it to a list, okay? Now, I don't even have to technically do that. By creating that task and calling add rectangle, it starts the task, right? And since I'm not awaiting on it, I'm going in a full speed loop and creating task, creating task, creating task. I'm creating all the 70, 80 tasks that I need in a quick cycle. And then at the end, I am calling task.whenAll, which essentially returns a continuation task that pauses and waits until all of the tasks have completed. And in this case, I just write out the word done, but technically I didn't have to necessarily even do that. All right? So by being conscious of where you place your await keyword, you can start multiple tasks or kind of delay the starting of tasks. This is also, this when all, this is the first kind of look at a combinator. And a combinator is a technique in which we can look at a number of different tasks and kind of look at them in an aggregate. So if I want to, say when all or when any is kind of like a when, just give me when the first one of these is completed. And that allows you to structure your logic based on that. And there's some really cool throttling examples that we'll see later. All right. So there's another one. Oh, here's the other browser. So I forgot. This is the one, since it's Silverlight, I have to open it in the old, I call it the old. It's the original IE instead of Edge. All right, so just search for Async 101, and this returns, there is also code available, but I like this one because it's a Silverlight app, and I can use it in my browser and actually test out the logic there. But I don't know if it's going to be readable. All right. So this has both C# and Visual Basic kind of examples of a lot of these different tasks. And then you can kind of go through them and see how they work. So kind of playing off the one we just saw here, we have await on our web client, download string. So this really does the same, very similar to that first example we showed where we're going out and getting the weather and then writing out the page title. We can also do this serially, same as we did with the kind of rectangles where you do an await for each one. And then if you want to take this and then switch it over to the parallelized version, it's just a matter of delaying when you call the await. So by going out here and firing off all the tasks, one after the other, now all 3 of those tasks have started. And then from there, I can await them individually. Now, in this case, they may not return in the same order. So in this case, I might actually get page 3 first, and then get page 2, and then get page 1. But given the way we've structured this, I'm not actually going to look at those until page 1 comes back. So despite it being executed in parallel and all the calls are made in parallel, the listening for the responses is then sequenced again. There's another technique in here where you can do this without being conscious of the other threads that are going on. UI responsiveness, there's not too much there, but cancellation is a cool one. So in the case of cancellation, what you do is you create this new cancellation token source, and that's going to be very similar to our task completion source. The source itself is the one that's in charge of doing the cancellation, but the source also has an object on there called a token. So I can take that token and I can pass it into any task. And what's nice about this token is that all the frameworks have been plumbed with this additional parameter. So everything within the .NET framework, from network calls to disk calls, they're all going to support the same type of cancellation. And what I can do here is then at any point, I can call this cts.cancel, which is this kind of cancel button here. And if the source calls the cancel, then what will happen is the caller here will actually throw an operation canceled exception. All right? And there is an option here on the token. So if I take a quick look at this, let's just create a token so we can see this. All right, so the cancellation token source has things like cancel or cancel after. Cancel after is nice for kind of timeout situations that you might have, whereas cancel would be more something that you would have in a button click, right? So if you did have a cancel button, you wire that cancel button to call cts.cancel, and then the task will get the cancel notification when you call cancel. Now on the token side, so once you've passed in this token, again, the frameworks have done this already for you, but if you're writing some code where maybe you're doing a for each loop over 1 million items, and you want to listen out for this cancellation token, you let them provide a cancellation token as an additional parameter, and then from there, you can say, is cancellation requested, which just returns a Boolean, or what would be more common is you just call this method sporadically throughout your processing, where you say throw if cancel was requested, and what that does is that throws that exception we saw before, which was called the operation canceled exception. So if you're ever building any framework code, or you're building some sort of an async method that's expected to be called by other people, you should consider adding an overload that provides cancellation, and then allowing that overload to pass that into any framework async that you're doing as well, to allow that to happen. It's a kind of forcing you, if you ever write framework code that's asynchronous, you should have multiple overloads of that framework code. All right, here's an example of that synchronous bound one. So here, when you run this process async, which is the same as the task, then sporadically throughout the loop, they're just checking for the throw if cancellation was requested. Cancel after, I prefer timeout, but because I think it's a little more fun to see. Oh, actually, this is the one. So in the case, is there a timeout also? I'm sorry. Okay, this is the one I was looking at. I might do the timeout one afterwards to kind of show this. Cancel after is going to be very similar to the timeout one. All right, progress. So progress is an event that's handled as part of it, and it works really the same way as cancellation. we have a kind of an event handler, an event progress, and that has a method on there that allows us to report progress. So you take that object and you pass it into your task. Your task then calls the function on it, which then would return back to you. So here we have an event here called progress change. So as the caller, you create the event progress, you register your event handler to listen for when a progress changes, and you pass that progress item into your async function. And then in the case of this get pings, you will see here, if progress doesn't equal null, then we're going to report some sort of result about our progress. So this is kind of reporting the percentage there. Trycatch, there's not really much here except to say that it works and it's awesome. You call await and it actually fires an exception, which is incredibly difficult to do or to have done in the old task ways. So when you're looking at the example where we had the rectangle that had the recursive for each loop, for eaches and while loops are one example of where things get extremely complicated before we had async and await. Debugging was another one, and then the other one here is this one where we try to handle exceptions. Because what you end up having to do is every anonymous function has to have their own try-catch handlers, and you're checking for exceptions in one and not the other, and it becomes kind of difficult to manage the exceptions throughout all those different processes. All right. This one was, no, I thought this one was a different one. So the combinators are, the one I already showed you was the when all. It's essentially a way to pause in an asynchronous way, pause until all the operations are completed. And then there's when any, which is kind of a single version. And with when any, you can do a ton of different things. The throttling one, this is similar to the one I had, and what they're doing in this case is they have a variable set for the concurrency level, right? So we have a concurrency level of 4, and then we have a list of 20 items, I think. And what we're doing is we're for eaching all of those, and for the first one, we're gonna add 4 items. So right off the bat, kick off the process, start running all the first 4 tasks. After we've done that, we're going to continue until there's no more tasks left. And we're going to do a when any. So we're basically saying, if we have a block of 4 tasks that are executing, once one of them's completed, we'll pop that off the stack and we'll add the next one on. And then we'll loop again. And okay, when any of these are done, then pop that off the stack and put a new one on. So we're essentially looking at this bucket of 4 items that we're going over in a for each loop. And as soon as one of them is finished, we put another one in its place. All right? So it's a kind of cool way to manage that throttling. In the previous example, I just threw all the rectangles at it. But this gives you a way to kind of say, I can do more than just one at a time, but I don't want to do them all at once. Let you manage that. I think the last one I like to show here is the timeout and the retries, because I think they're just a kind of cool way of doing it. So timeout. Essentially, what we have here is we're calling into a function and we're saying, run this operation and then timeout after 30 seconds, or through 3 seconds. So this timeout after, what this does is essentially says, and ignore the task ex, but the task.whenAny, so let me know the first task that completes in this race between the task that you provided and a delay task, right? So it sets up this kind of, let me know the first one's done if these 2 guys go and race, right? And after the race is completed, I'm going to check to see if the task was the one that won, right? So did the task win the race, or was it the delay that won the race? And if the case the task did not win, then we throw a timeout exception, basically saying that the delay was the first one to win, the task hasn't completed yet, and go ahead and throw an exception that it timed out. So for the first time I saw that, I thought that was a kind of cool way of using combinators to do timeouts. The last one here is retry, which uses a bit of the timeout mixed with a loop. So you're essentially saying retry this timeout task 3 times. And then with that, think it's just managing all the exceptions, but we're really, and that's probably not the best way. They should really be looking specifically for that timeout exception. And if the timeout exception happens, then we check to see if the max tries are done. Otherwise, we continue and try to process the function again. All right. Any questions on those? All right. On to the fun stuff, the compiler. All right, so for any of you guys who have done async, we're done with the kind of level setting. Now let's talk about the magic about how this happens. So, oh, not there yet. So if we look at another example here, this is a very common pattern that is it's called custom iterators. It is a keyword called yield return, which allows you, is really the underpinnings of the technique that's used for this async and await keyword. So again here, we're in a situation where I'm returning a string, right? But for some reason, this method is defined to return an IEnumerable. And I'm not returning an IEnumerable, I'm returning something different. So the compiler is doing something underneath the covers to convert this multiple strings into an IEnumerable. All right? So what's happening there, and there's a couple ways I can show this, but I'm going to try to show it off the manual way. So in the case of reading this out, typically what you do with an IEnumerable is you say for each. So we're for eaching over all of our letters, and then we're calling console.writeLine for that letter. What's actually happening, given that it's an IEnumerable, is it's calling that function, get 5 letters, and it's calling the get enumerator on it. And that get enumerator is something that we can actually look at, we can actually call 2 methods on it, either move next or current. So in the case of this loop up here, the for each loop, the first thing we do is call move next, and then we set the letter equal to current, and that's what it's doing. Same way we're doing it down here, where we're calling move next, and then we're setting the letter equal to current, and then we're writing that out. Right? So these 2 blocks of code are essentially the same thing. When we look at how this works with this move next and this letter, that's really what the compiler is having to map to, or what it's having to generate. So if we look at the manual kind of version, and so I've taken this and I've taken the liberty of kind of recreating it as if the compiler is recreating this. So here we have the same code as before, where we're for eaching over the 5 letters, and we're writing out each letter. But our get 5 letters, instead of having yield returns, is actually returning what you would expect, which is an IEnumerable object. Now, this IEnumerable object, which is get 5 numbers IEnumerable, is a compiler-generated class, and it wouldn't actually have this name. It's going to have a bunch of other funky characters on there, characters that I actually couldn't create and have a successful build, but is also there so that you can't actually call that. So they put special characters in there so that I couldn't actually call the compiler-generated classes. Now, this compiler-generated class essentially inherits from IEnumerable and IEnumerator, and it has those methods. So in the case of the IEnumerator, or an IEnumerable, it has a get IEnumerator, which in this case we're just returning ourselves. And then the IEnumerable is really the core to it, the one that has the move next and the current. And the current one, and so the current one is just a variable, but the move next is where all that magic happens. So if we look at the way the move next worked in the for each loop and the yield return, the first time we called it, it went into the yield return and did a yield return of A. Right? So the first time we call move next, we haven't actually done anything yet, so our state is 0, and we're going to get launched into this state where we're going to set the current variable equal to A, and we're going to increment the state one more time. And then from there, we'll return true. Now, the next time we call move next, we're going to be in state 1, and we'll set the current equal to B, and we'll increase the state, and so on and so forth. So essentially, it's creating a compiler-generated class that is acting as a state machine. And every time I call move next, it's moving on to the next state, which is the state in the line of code that we wrote for our iterator. So if we take this and we look at this yield return, it's treating each one of these lines of code as a different state. And one of the fun things I'll do sometimes is I will do this exact same line of code, and I'll say console.write, and I'll put in, like 1, and I'll put in a few other kind of tricks to this. And then I'll ask as an interview question, what's the order, what's the output here, right? Because what could throw you off if you didn't know what was happening here is one might think that it's going to run all of this function, and then it would loop through and write out the letters, right? But the reality is this yield return is breaking this up into different states at each yield return, right? So what's going to happen is it's going to call move next, it's going to get into A, then it's going to call 1, and then get to B, and then it's going to call 2 and get to C. And so understanding that it's using the state machine was an interview question I would commonly use. All right, so that there, custom iterators, this was actually used by a gentleman named Jeffrey Richter out of Atlanta, who created this thing called the async enumerator. And what he essentially did was he took this pattern and he combined it with the async programming model, and took this technique in order to have the underlying async enumerator automatically handle the move nexts, just like and handle the begin and end reads using this custom iterators technique. And that's why I'm bringing this part up, because him using this technique is actually the same technique that was then migrated over, and he ended up helping out the .NET team to create the implementation that they're ultimately using now for Async and Await. Just to kind of show that this is accurate, I do have .NET Reflector here, and .NET Reflector is a disassembler or a decompiler that allows you to look at the actual source code. So in this case here, we have our same method of get 5 numbers, which should be here. And you'll see that compiled as .NET 4.5, that this is actually a bunch of yield returns. Now, if I change this to say .NET 1.0, before custom iterators were invented, you see that it's actually a different code, right? And now we're in this scenario where we have this new compiler-generated class called get 5 numbers, and then that's what we're returning. There is also some extra work in here that's interesting to look at, but one of the challenging things of managing these things that are in a single block is that you have to now support closures. And closures are a way where you can take objects that are either on the stack or even objects that are within that class and pass them in to your, and use them as part of your function. Now, if I create another class, I can't go access things from the stack. And I can't access things from the other class. So by passing in the other yourself to the new class, then that class has kind of a reference to the original caller where it can then access things on it. And then if we look at this method here, or this class here, we go this way. You'll see we have a state and a current, just like we saw. In the move next function, you'll see the same basic code that I wrote there. Can I enlarge this? Yeah. Which is our state machine. And we have a switch statement that says, okay, if it's the first state, then set the current to A, set the current to B, set the current to C. All right. So how does the async one work? So here we have another task. In this case, it's just a task called getWeather, and then it's returning our download string task async. From here, we're going to go ahead and call into our download weather. Actually, sorry. This is the one we're looking at, download weather, which is an async void, and we're calling in await on our getWeather, and then we are writing out the page title for that page. So similar to the way we did it before, here's a manual kind of version that shows that off. Our download weather, instead of what you saw before, which had the await keyword, what we're doing is we are defining an async method builder, which that's the controller that's going to be responsible for managing when to call next and when not to. And then we have this, again, this compiler-generated class. In this case, it's called the download weather state machine. Now, with that, we're again passing in some references to other things, and then we're telling it to start and to kick off the initial state for that. Now, from there, we get into our class here. And just like you would have seen with the async enumerator, we have a move next call. And in this move next call, we have a state of 0, which is going to execute the first half, which is this download string async. So I have that a little bit backwards. I actually would have had it. Let me just rebuild this. But the point is that at this await keyword, this is where we're chunking things up a little bit differently, right? So the reality is, and it's tougher to explain this way, but let's say that this here is a task, and then we're awaiting on this task. So essentially, where our states break apart is here and here. So we're saying, first off, this is state 0. Go ahead and start off the function, call our getWeatherHTML, and once that is completed, since this is a task, once it's completed, I'm going to call move next and get to my next state, and then this is my next state, where I'm looking at the result of the task, which is a page, and then I'm going to get the page title from there. Let's see if this refreshes at all. Oh, that's why it wasn't refreshing. I'm sorry. This is code I wrote by hand, so yeah, it's not refreshing because I wrote it. So fire that guy. All right, so essentially the same deal though. We have an initial state, and this initial state calls up until the beginning of the await. So at the beginning of the await, once we get this task back, we have a little bit of an optimization check. And this is the one I was mentioning before, where we're going to check to see if that task is completed. If the task was completed, we're just going to call move next, right? So it's already completed. It happens synchronously. We'll just move next, and we'll move on and keep going. In the case that it didn't complete yet, and so it's actually off and it's still running somewhere, what we're going to do is we're going to get the awaiter from that task, and we're going to say, whenever this awaiter completes, then call move next, right? So we're essentially setting up a continuation to say, when this task completes, continue with calling the move next function. And that allows us to do that multiple times, where we can continue with and then move next and continue with move next. And it's calling back into that move next with every continuation. All right? So in either case, whether it's calling this move next or this move next, it's going to come back in. In this case, our state has incremented as it did up here. And now we're in state 1. So when we come back into move next, we're in state 1, in which case we get the result from our last awaiter. And we execute the remainder of the function, where in this case, we're writing the get page title. Now, I mentioned a little bit about the closure, and here's where you're seeing that, right? So we had get page title before, which wasn't actually, which was on the class. And now that we have a compiler-generated class, which is a separate class, we need to maintain a reference to that previous class so that we can call back into any methods that are being called. All right? So again, just to kind of show that I'm not fibbing to you guys, here we have our async downloader, decompile, and you'll see here our download weather void is actually creating a new compiler-generated class with the same name as the method, called download weather. We are creating our async void method builder, and then we are calling start on this state machine. Now, from here, we have our state machine here. Again, compiler generated and got the funky characters. And if we look at the move next, you'll see that we have task number 1. And in task number 1, what did I click on? So in task number 1, we are calling here, this one up here, getWeatherHTML. So getWeatherHTML is the task that we had the await keyword before, and that one it actually returns a task. And with that task, we're going to go ahead and get the awaiter. And then with the awaiter, we're going to check, the awaiter has the completed just the same as the task does. But the awaiter, we're going to check if it's completed. If it is, then it'll continue on. So it actually doesn't call move next in this case. It's going to use an else. And then if the completer, if the awaiter has not completed, then it's off running and we need to call back into move next. And that's what we have here where we're saying, unsafe on complete, and we pass in a bunch of stuff. But essentially we're saying, whenever this awaiter completes, then we're going to call into our state machine move next. So my version was a little bit simplified, but you see how much is happening underneath the covers for something simple like that download weather function that we had. All right, makes sense? Did anybody here know that all that was going on under the covers? All right, so this gets to our next part here, which is the kind of tips and tricks. So always allow async tasks to bubble up, right? This is the mentality that async void is bad, right? Async void and async task are completely interchangeable. In the case of this example here, where we had our async void weather here, I could also call async task weather. There is no difference whatsoever to the inside of that function between async void and async await, or async task. The difference comes mostly in the caller of that. And if you use async void, then the caller is pretty much chopped off at their hands. They have no recollection or understanding of when things are completed, right? So kind of circling back a little bit to what we had said in the beginning with the console, with the reading of the streams, how that method ends. Given that this is an async void here, then our method's going to call this task, and this task is going to complete. Once this kind of await happens, this method actually completes. So whoever called this download weather gets a response back even though nothing has actually been completed. So if I end up getting an exception down here on get page title, there's no one who's keeping track of that exception, right? I would only get notified of exceptions that happened before the very first await. And that's obviously not helpful for most production code, so we want to always use async task to make sure those bubble up. Question?
If you're calling into an async void method, does it block them? Or
no.
It doesn't.
It's a fire and forget. So, and it's a fire and forget to a point. It's a fire up until the first await. So again, if there's a task in the initial part, then you'll still get, or an exception, you'll still get it, but otherwise, those exceptions are lost to the wind. Which makes it very challenging when you do talk about UIs that have only event handlers as their mechanism for callback. So a button click would be async void, but essentially I have to then from there make sure that what I call plumbing the task all the way throughout the framework, right? So if you have a UI and then from that UI you're calling into a business layer and then you're calling into a data layer, you want to make sure that from the UI on everything is returning async task as opposed to async void. Okay? The next one is to use configure awaiter, especially if you're using a framework or any non-UI code. And this came up to the question that came up earlier about is it returning onto the UI thread or is it returning onto the same calling thread? By default, async and await code is always going to return on the same calling thread, which means it can have a context switch before that happens. And you might actually see it in here. No, it's probably, we could drill in and find it. I think it's inside either the awaiter or one of the method builders. But the point is that there is extra code at the very end of that task to make sure that we switch back to the original context that called it. And that switching is actually quite an expensive process. So if you're writing framework code and you don't really care about making sure it comes back on the UI thread, or if you're in the same scenario where you have a UI and then you have a business layer and a data layer, well, the data layer doesn't have to worry about doing the context switching. You only need to do it on the closest one. And so you can use a method called configure awaiter to tell the await whether you want to return on the UI thread or not. So in the case of our download weather, where I'm awaiting this task, I can say await task.configure await. and I can configure await for continue on captured context. So I can say false, which means continue on, and just come back to this method on whatever thread you were on when it came back, right? So it allows you to just be flexible and be a little bit more performant when you're talking about framework code to never actually go back to that UI thread if you don't have to. All right. The next one, don't overuse async and await. I see this constantly, and I always, I can't help myself but kind of do this. So you want to, if you have a method that has a single await statement, and that await statement is the very last statement in the method, then there is no need for async and await. In this, do I have it here? That's why I created this here. So what will often happen is people will call async on this task, and then they'll call await on here. All right, so what we have here is we have this thing that's this string that I need back, and I will say async task for the string, and then I will await on this download string that is then going to return. Now, in this case, there is only the single async and await. So by adding this async and await here, I have created a whole compiler-generated class that has a state machine and executes things and handles the closure references in an odd way, or let's say creative way, when I don't need to at all. All we really need to do here is just return the task directly. So in this scenario, I can take out the task, the async and the await, and just leave it this way. So this here, which is returning a task, is just going to come back as a task automatically. This happens a lot when, if you ever do like a repository pattern where you maybe have some sort of a database connection, whereas some cases you'll get some information from a database and you need to manipulate it before it goes back, whereas some cases you might send the data back directly. What I've seen a lot of architects do is kind of set up the structure where everything's kind of async and await, and people end up just kind of filling that structure in, and then don't realize in half the area they don't need it, and half the area they do, right? So just to kind of try to drive that one home a little bit more, let's just put a couple console. So there's a couple nuances to it, right? So let's say that this is a task, right? And then I want to even do some more stuff afterwards. No. And then return the task. And then let's just add a second one just for fun. All right. So in the case here where I have two different tasks, and let's say I await this one, and I await this one. All right. This is totally valid, right? I have a situation where I do have a state machine. I'm calling into, I'll leave that for now. I'm calling into one function to download a string, and then I'm going to do some more code, and then I'm going to call into another one and some more code, and then finally return the string here at the end, okay? Now, in the case that I only had one await statement, right? So let's say that we've now kind of removed this one. The initial clue is, all right, do you only have one await statement in your method? If you only have one await statement, there's a possibility that you don't need async and await. If your await is at the very end, right, and we're returning, something like this, where we say, go ahead and return this await, then yes, by all means, you are going to need to have the async, if this is at the very end, then you can pretty much guarantee that you don't need the async and await. If the await's the only await and it's at the very end, you don't need it. If it's in the middle here, you may or may not need it. So given it's the only await statement and it's in the middle, it depends on what happens afterwards. So if the stuff that's happening afterwards is using this result, then yeah, you still need the await. If it's not, and for some reason, I don't have all the understanding of what cases it might not, but if it's not actually using anything from this, then instead of the await, I can actually have this result be a task, and then again, I can go ahead and just take this off, right? So if I don't have, that's a result. And then there's no compiler-generated logic going on here at all. It's just going to return the task directly, just like any regular .NET code would. All right? So does that make sense? You guys are all going to go home and check your code now, and I'm sure everyone's going to find at least one place where you have that happening. All right, the last one on here. Don't be afraid to just create tasks directly, right? The very first example I showed with the task completion source, in some cases, and you may be able to write your code a little bit more efficiently than async and await would, right? So async and await is very nice to read sequentially and has a lot of has a lot of help when it comes to doing for each loops and exception handling and all those things. But it's not necessarily required all the time, right? You don't have to use async and await everywhere. You don't have to plumb it throughout. Understand that there are some penalties to using async and await in the sense that it's creating a separate compiler-generated class and doing context switching all along there. And so if you want to create your own task completion source, manage the life cycle throughout your own smaller process and have that returned, I would recommend that to consider that. If the alternative is to have hundreds of compiler-generated classes as opposed to maybe a more concise single one. All right, and with that, I got a little bit of time for are free. I got you out 2 minutes early. Yes, question in the back.
I think that's always the kind of the case which is skipped over. If you have, for example, an interface that you need to implement, which is a void method, so you cannot change the return type. So you cannot make it an async method, or you could, but you shouldn't. How would you handle calling async code there? Because if it's an async net application, you cannot use result because of the task method. So how would you have a void method, call an async method, and basically await it without using await, because you cannot use await because you cannot use async.
Right. So the biggest downfall is exception handling. There may be other cases in case of, you mentioned running tests. That's another scenario for sure. In the case of exceptions, the general rule is if you have async void, then put a try-catch. So every time you have async void, you should have a try-catch. Or you should create some sort of mechanism to kind of trap that going forward. And then also, if you're creating any new interfaces, consider having task as a return type for new interfaces, for sure. But the tests one is definitely a tricky one. If you have async void anywhere, it's going to be near impossible to test that directly. And what I would recommend is you create a kind of, in your implementation of it, you create something on the side. I don't know, you might not have the ability to adapt your interface, but if you could adapt your interface and kind of do a side-by-side and then proxy your async void into the async task, then you still test your async task. But you're not going to be able to test async voids. It's going to be a problem. Any other questions? Yes. Yeah.
So that example you gave, the second at the end, about if you have one line and you don't have to use async await,
Yep.
you would still want to name it whatever async, right?
Yeah, anything that returns a task object by the convention has an async ending. Yeah. Yeah, and so that's the other thing too, is to think of these as the task return type, not is the kind of the definition that drives that decision, not the async await keyword that drives that decision. Yeah.
As far as configure await, abandoning the context, do you want to do that at every level where you're using a task, or just at the high level?
Every low level.
Okay.
So the high level is the only place you don't want to do it.
Right.
Yeah. So yeah, because then that way you're back on your UI thread. In the case of ASP.NET and web services, you do it everywhere. I have not seen a case in ASP.NET where you would want to not use configure await. Because async and ASP.NET is running on a bunch of different threads, and it doesn't care what it returns the requests on. That doesn't make a difference. Yeah, I forgot to mention the ASP.NET one, but that's I kind of wish that had been considered more, because I feel like there's probably more code bases out there that are ASP.NET based than WPF or Windows 10. So I used to do a lot of talks on Windows 10, and sadly it didn't get adopted as much as I wanted it to. Still working on it, I guess. The new thing is HoloLens will drive Windows. So first, Windows Phone was going to be revolutionary, and then Windows 8 was going to make Windows Phone good, and then Windows 10 was going to make Windows 8 good, and now HoloLens. We'll see. All right. If there's nothing else, you guys can enjoy the rest of your night. Thank you.